Okay, welcome. This is video 1 for the drivetrain unit notes. I want you to be able to calculate static and kinetic friction, discuss different types of steering systems, and explain turning torque and turning scrub. Okay, so to get us started here, we need to talk about friction. This is one of the most important parts when you go to design a drivetrain. Friction. This is a force that opposes sliding. So, a couple things about friction. It's a reaction force only. So, if an object is not trying to move, there will be no friction. Secondly, it only happens when we have two surfaces in contact. Now we have two types of friction. We've got static and kinetic. Static means stationary. So for static friction, the objects do not move. They're trying to move, but they don't actually move. Kinetic means motion. So for kinetic, we have two surfaces that will be sliding past each other. Now, we can make a plot of this. Let's say we have an object. And we have a person trying to push on this object. We can say then that there will be an applied force, and opposing that will be a friction force. So as the person starts to push, friction, static friction between the two surfaces grows. It becomes stronger and stronger until we reach this point right up here. This is the maximum static friction that can exist between the two surfaces. Once we reach this point, the object will break free and begin to slide. And this is where we get our kinetic friction. Notice that the kinetic friction is less than the static friction. So it's easier to keep something sliding once you've broken it free. What friction does is it converts mechanical energy into thermal energy. So whenever two surfaces slide past each other, we get thermal energy. The surfaces will begin to heat up. The way we calculate friction is we take something called the coefficient and we multiply it by the normal force. And what's kind of neat is that this formula works for both static and kinetic. So for the maximum static friction, we get this coefficient of static friction times the normal force. And for kinetic, we get the kinetic coefficient of friction times the normal force. The mu, this letter of mu, we can think of it as how much grip the surface has, how sticky it is. Okay, now for the normal force. We really have to be careful with the normal force. When we take a look at an object at rest, we know that there's a gravitational force pulling down. There's also a normal force pushing up. And what the normal force is the force of the surface pushing on the object. So what makes this tricky then is if we have something sitting on an incline. the force due to gravity is still vertically down. But if you think about it, the surface is pushing in a different direction. You see, the word normal means perpendicular. So the normal force will always be perpendicular to the surface. A final note, this is kind of a fun experiment you could do. If you want to know what the maximum static, or what the coefficient of static friction is, what you could do is you could set something on an inclined plane, and you can adjust the angle. And as it turns out, tangent of the angle will equal the coefficient of static friction. And if you want, I can derive that for you if you want to know where that comes from. But it's a really cool way of finding out what the coefficient is between two surfaces. Now we can use this for something called traction. This will be the amount of friction between the drive wheel and the surface it's rolling on. We can think about it as the amount of force a wheel can exert on a surface before it begins to slip. So here's what we have. We've got a wheel, and we have a motor attached to it, so we have a certain amount of torque acting on it. Okay, this wheel has a radius, and what we want to look at this point right down here, right where it meets the surface. So some forces we have. We have a normal force. We have a gravitational force, and remember, we can calculate that with m times g. And if this wheel is trying to rotate counterclockwise, that means that it's going to exert a force in this direction. That means that friction is opposing sliding. So friction actually points forward. And this is really counterintuitive. When you have a wheel under power, the friction goes forward. So we can do a little bit of math with this. We want this to stay in equilibrium. So what we want is this force to be equal to the maximum static friction. You know, when this happens, we are at the maximum amount of traction we can have right before the wheel begins to slip. Okay, so torque, remember, is a force times lever arm distance, and in this case, lever arm distance is the radius. So this force equals torque divided by the radius. Friction is coefficient times normal force. So this is going to be US times the normal force. And finally, looking at our diagram, we can see that the normal force equals how much the object weighs, so equals mg. So what we're left with then is torque divided by radius equals mu s mg. And this is our equation then for traction. So some things we know, we can figure out the torque. We've been doing that in class. We know the radius of the wheel. We should be able to look up the coefficient of friction between two surfaces. G is always 10, and we should know the mass of our robot. So we should know all of those things, and we can figure out if we have enough traction. So what are some ways of increasing traction? Well, looking at that equation, we could increase the mass. We could decrease the torque. We could increase the coefficient. And looking at it, we can play around with the radius of the wheel as well. I'll leave it up to you to figure out if we need to increase or decrease the radius. All right, so let's say we want to build a robot for pushing. we want to be able to push or pull with a great amount of force. So the robot's going to need two things. It's going to need high traction wheels and a large amount of torque. Being a reaction force, um, with friction, if there's no applied force, then there will be no traction. So to maximize traction, the torque applied to the wheels needs to be enough to reach the maximum static friction. So we want to be right at that tipping point, right where we have just enough traction. So something to keep in mind, in the real world, a car can have all the traction it needs, but if it has a small engine, it won't be able to push or pull anything. This is why we don't use small cars to tow large trailers or boats. Now in the VEX system, we have a variety of components for gaining traction. We have several types of wheels. Each wheel has a different characteristic on different surfaces. So as a designer, you need to experiment and choose which wheel is best for an application. Now, friction between the wheels and the floor is not the only friction that's relevant. Friction can also act as a brake on the rotating components. So you want to make sure that you reduce friction in your gear trains. Make sure that the spacers aren't too tight. Make sure that you're using those white Teflon low friction washers. Well, that concludes video 1.